Flaticulation laser cutting joints with articulated angles on behalf of his team at National Taiwan University.
Hello, I am Chiao and I'll be presenting Flaticulation. This is done with my colleagues Vivian and Longpan when I was in National Taiwan University. Flaticulation is a method to laser cut joints that clutch two cut-in-place boards at designated articulated angles. This allows fast assembly of laser-cut 3D objects, simply folding cut pieces till they clutch. Our motivation is to quickly fabricate complex objects. Laser cutters are great in this case. It fabricates much faster than 3D printers, but since it cuts in 2D, extra effort is required when making three-dimensional objects. Joints are necessary when forming 3D objects using laser cutters, which requires additional modeling effort. Hands-on assembly is also required afterwards. Previous work have provided interface to embed joints into design or direct conversion from 3D models into various laser cuttable plans, such as using cubes as basic building units or planar cross-sections with mesh joineries and lamination for building mechanisms. Nesting laser cut pieces have been proposed for faster hands-on assembly. However, most joints connect well only when boards are perpendicular. This makes it difficult to fabricate complex polyhedral objects, requiring clamps or adhesive to assemble before holding the supporting parts. In the meantime, these joints cannot be cut in place. In other words, the connecting pieces have to be laid out separately to account for the laser cutting curve for a tight fit. Flaticulation introduced new joint patterns. The joint clutches two cut-in-place pieces at predefined articulated angle by just folding them. This enables easier way to assemble unfolded 3D polyhedral models and also add detent hinges into laser cut objects. Here is the workflow of making a computer mouse in Flaticulation. The user starts with a low poly model of a mouse in a 3D modeling software. Once our user face in Rhino then inputs the 3D mesh and unfolds it automatically. Parameters, the joint patterns corresponding to the angles would be added to the unfolded pattern. And parameters such as the laser cutting curve and the material thickness can be adjusted in our user interface. We then locate the mouse button of the mouse button location and to add a detent hinge. The detent hinge would provide tactile feedback when the button clicks. Detent hinges can be added through our user interface by selecting the segments. The user then adjusts the angle of detent and stiffness parameters to tune the tactile feeling of the mouse clicks in our user interface. Finally, the mouse can be laser cut and assembled easily by simply folding pieces to clutch at the correct angles. We demonstrate flaticulation with various two-manifold models by unfolding the 3D models automatically, such as a wolf hat and a Stanford bunny. The models are assembled by folding every laser cut pieces. Non-manifold model can be also designed directly using our interface in 2D. Here we made origami-inspired crane and a boat. With detent hinges from Flaticulation, we also built functional objects that have reconfigurable structures. I will now introduce the special laser cut patterns in detail. Two kinds of patterns, which we call T patterns due to its shape, is the foundation of Flaticulation. The less than theta T pattern only allows motion with angles less than theta, which is in this range. And the greater than theta T pattern has a snap fit mechanism, and it only allows motion with angles greater than theta, which is in this region. The intersect of the range of motions between these two patterns will be exactly the desired angle. An articulated joint is therefore achieved by placing a less than theta pattern next to a greater than theta pattern. Let's have a close look at the patterns in action. Here you can see the two patterns. The greater than theta pattern in the right snaps, and the less than theta T pattern in the left limits further movements. So the two patterns work in unison to clutch the boards correctly. Besides articulated joints, flaticulation also makes detent hinges using a laser cutter by lining a greater than theta T pattern with a living hinge. This clip shows the detent hinge working, and the force here you can see there's a detent force when the hinge moves to the specific angle. Next, I will talk about the geometry of the cut-in-place T patterns that enables flaticulation. The patterns create a latch to be jammed with the material thickness. This is the cross-sectional view of the patterns to get a better idea of the joint, and I'll introduce them separately. First, we'll look at the less than theta T pattern closely. Here you can see the geometry, and the moving gray boxes indicates the range of motion of this pattern. And the green dot over here limits the motion with the collision of to the gray boxes. So therefore, the position of the green dot determines the theta angle of the pattern. And we get the position by solving the intersection of these two lines. Next, let's look at the greater than theta pattern. Here you can see the head of the pattern first snaps, then rests on the top surface of the board. The position of the green dot will be the final laser cut position. But to get the position of this green dot, but to get the position, we need to look at the orange triangle first. And we can get the orange dot's position with trigonometry. Then the green dot is extended out from the orange dot to achieve the desired snap. We also looked into the effects of the curve of the laser cutter. We found out that this should be also considered when calculating the geometry. The laser cut curve creates small errors on the T patterns, like these areas. We therefore look into these and consideration in the geometry, and the details could be found in our paper. We performed experiments to evaluate flaticulation joints, in particular, testing angular error and the strength of joints. We tested 5 different angles with a total of 100 samples, and the average error is around 3 degrees, which is acceptable in our cases. To examine the strength, we first conducted simulation using finite element analysis. We simulated the joint under load of 2 directions, being pushed down and being pulled up. We identified the location where the maximum stress occurs, and the actual failure point matches the simulation results, and these parts should be strengthened for making stronger joints. We also tested different configurations of the joint in simulation. Using joints on thicker material results in better strengths, and widening the pattern also have similar benefits. Finally, we mounted the joints on the tensile testing bench and put torsional load on the joints to test its strength. We tested with 16 different joint angles and compared the results. We plotted the maximum stress of each joint, and the blue line indicates the joint being on push load, and the orange line is the joint under pull load. The joint should withstand at least 1.5 Newton centimeter of torque from our empirical testing. So here you see the joints with the angle in the range of 0 to 15 degrees and 90 to 103 degrees are weaker than that. So these are less useful. But for the other joint, it worked well and withstanded loads up to 34 Newton centimeter. Here I will talk about some findings and limitation of flaticulation. In our experience, repeating the pattern gives a stronger joint. However, we did not successfully run simulation in finite element analysis on repeating patterns to confirm this. So more tests would be needed to optimize flaticulation joints in the future. We also observed that the strength of the T pattern is not symmetric. Like it's weaker here but stronger in the middle. So this hints that arranging the pattern might lead to better strength of the joint. And it seems to be the case in our preliminary experiments. And speaking of folding sequence, most models can be folded in any order. However, some convex models like this one encounter obstruction because of the folding sequence. So this can be resolved by unfolding a joint and inserting the obstructed pieces, then folding the whole thing back. And this process could be automated in the future by searching the collision in simulation automatically and giving users instructions on the feasible folding sequences. In conclusion, we propose flaticulation and articulated joints that make fabricating complex structures using laser cutters easy. We presented a user interface and analyzed the geometry and validated our technique with experiments and demonstrated various examples. Yeah, thank you for the listening, and please join us in the demo booth tonight.
Okay, let's thank our speaker. If there are any questions from the audiences. If you have any questions, please stand up here and then introduce who you are from where you are so that we can know who you are.
Okay, thanks for the very interesting work. I'm Came from Digit South Korea. And Digit, my question is, did you test the effect of the various materials? So relationship between the materials and the strength, the functionalities.
Yeah, so we also tested out on acrylic, and it has slightly stronger strength, but it's more brittle, so it breaks really easily. So we did most of our prototyping on medium density fiber boards. Yeah.
So do you have any optimal material recommendation?
We think that the MDFs works quite well in our cases. Yeah.
Thanks.
Hi, I'm Koya from the University of Tokyo, and first of all, congratulations. And I
Thank
have
you.
several questions. So first of all, what is the maximum folding angle, and is it restricted to the thickness, for example?
The maximum folding angle we did like 160 degrees, like folding for 160 degrees, and I think it can go even further, but the problem would be the joint would be very long. Yeah, but we can get that angle.
So is it related to the thickness of the material?
Yes, also thicker material would have longer patterns.
And another question is, I'm curious, why don't you try more patterns like Mira-Ori or water-bound patterns, which has a low degree of freedoms? Most of the twist pattern is like a lot of single hinges connected together, but in reality, there are many origami patterns which has the dependent hinges with each other, with internal vertices inside. So did you try such kind of origami patterns?
No, we haven't tried them, but I think it would be really interesting, and also with the detent hinges, that would be quite interesting, I think. Yeah.
Thank you.
Okay, let's thank our speaker again.
Thank you. you.